Hello, I'm Lou Bloomfield and this is How Things Work. Today's topic, balloons. Balloons are interesting just in and of themselves, even when they don't float around. They're kind of light, fluffy things still. But they're even more fun when they float in air. So there are two classic types of balloons that float in air. One of them is hot air balloons and the other is helium balloons. And today, I'm going to talk about why those two special kinds of balloons float in air. In fact, what does it mean to float in air? So, to start the story though, let's look at air itself. So this balloon is filled with air, that one, and it's surrounded by air. What is air? Air is an example of a gas. It is a material that has no fixed shape and no fixed volume. It's one of two classic types of fluids. Fluids are, in general, materials that have no fixed shape. So gases have no fixed shape, they're a fluid. Liquids have no fixed shape, so they're also fluids. But the difference is, whereas gases have no fixed volume, liquids more or less do have a fixed volume. The details we'll come to later on, not today. But we're going to concentrate on gases today. Well, the first thing about gases, and actually fluids in general, is they can't just push out like with a finger and exert a force on something. Fluids exert pressures on things. That is, they exert a force per unit of area that they push on. So the air here is actually pushing on everything immersed in it. It's pushing on this table surface. Exerting quite a downward force on the top of this surface overall, but the force is exerted uniformly over the whole surface, in patches. And so a way of characterizing how the extent to which the air is pushing on this surface can be done by saying, let's take a certain area, the SI unit of area being a square meter. So you take a square meter of surface, and how much force does the air exert on that whole square meter? And that force per square meter is known as pressure, a pressure. And what is the value here? Well, in this atmosphere that I'm living in right now, that pressure is about 100,000 newtons on each square meter, newtons per square meter. It's actually quite a lot of force on every square meter, but that is the pressure that the air is exerting. You might wonder, okay, so how does air actually exert a pressure on anything? What is air? Well, air is lots of independent particles. Some of them are atoms. Most of them are molecules, which is to say atoms that are stuck together to create a more sophisticated or more complicated assembly than just a single atom. And these little particles move around with thermal energy. They don't just sit there inert. They have, each of them, a dose of thermal energy delivered statistically based on the local temperature. And because they have that energy, and really the only way they can manifest that energy, that's not quite right, but the primary way in which they can manifest that energy is as kinetic energy. So they move. They carry their little dose of thermal energy around as kinetic energy, by and large, and so they move around. And actually, they move quite fast. The average air molecule here around me is moving several hundred meters per second with its thermal energy. That's very fast. Well, why doesn't it zip across the room and head out the door? It's because they collide with each other. They're bouncing around furiously, hitting each other, hitting surfaces. All that business is going on rapidly, and they make very little progress, very little net progress across the room, even though they're traveling very fast on average. And as they bounce off each other up here, you wouldn't necessarily notice, but as they bounce off the surface, which they're doing all the time, they're exerting pressure on it. That's the origin of pressure, is that thermal motion of these little bouncy objects bouncing off the surface. And every time they bounce, they transfer some momentum to the surface. In fact, they're essentially perfectly bouncy little guys. That's not quite true, but they're very close to perfect bouncers. And so they hit and they rebound and they transfer momentum every time they do that. And with every momentum, it's an ongoing random statistical process. They keep pushing little impulses into the say the surface of this table, and that is where that's the origin of pressure. So, what are the particles in air? Well, the vast majority of them are nitrogen molecules, two little nitrogen atoms that are stuck together chemically and are relatively inert. We don't notice them chemically most of our existence. The other common, but not as common, little particle in air is oxygen molecules, two oxygen atoms stuck together. Now those are quite important to us because they're part of the chemistry that keeps us doing what we do. Oxygen is necessary for life. And then everything else is odds and ends, much less common particles, including some atoms, some true atoms such as neon and a tiny bit of helium, a tiny bit of some of the other, argon's also there in decent quantity. The rare noble gases, krypton and xenon, they're just barely there, but they're there. And carbon dioxide. And finally, water. Water vapor is present in here. Little particles of water rattling around, bouncing off each other, and participating in air's dynamics and the creation of pressure. All right, so that's what air is doing. It's a busy place, and it exerts pressure on any surface immersed in it. And you might think, well, if what I said, when I said that every square meter of surface down here in the atmosphere experiences a force of about 100,000 newtons, that's a lot of force. And you might think that this table, if it's exerting, it's close to a square meter, is it really experiencing a downward force of 100,000 newtons? Why isn't it crushed? Well, because there's 100,000 newtons of force down on the top, but from underneath, which is also exposed to the air, there's about 100,000 newtons per square meter pushing up of pressure. And the forces pretty much cancel perfectly. We'll see, not quite. If I take a sheet of paper and I hold it like this, they really do cancel perfectly. The pressure on the left side and the right side, they're identical. They push equally hard on one side as on the other. The forces have no interesting effect. One thing to point out, though, is there really is a compressive push on anything you put in the air. Like this sheet of paper really is being squished inward by a big force on one side, a big force on the other. And paper can tolerate that. People can tolerate that. Lots of stuff can tolerate that inward push. What can't tolerate it is an object that has nothing inside. Like, suppose I made a balloon like this with nothing in the middle. Empty space, a vacuum. In that case, there would be a big force on this side of the balloon due to the pressure exerted over that surface, and a big force on this side of the balloon because of its surface and the pressure over here. And those forces would be in opposite directions, and they would smash this balloon flat. Whoop! And that is why you can't you can't create a balloon that's full of nothing. You got to put something inside to keep it from getting smashed by the surrounding atmospheric pressure. Well, what do you put inside? More air. So this balloon has air inside that's pushing out with pressure that's essentially equal to the pressure of the air pushing in. And the forces all cancel. The skin of the balloon is happy, doesn't accelerate one way or the other. In fact, that balloon is an elastic balloon. It's made out of rubber. And so the skin of the balloon has some inward force just due to stretching the rubber. So it would like to get smaller if it could. And if those pressures, if the pressure inside and the pressure outside were exactly equal, the skin would be unsupported and would shrink, would pull inward. In order to stop that from happening, the pressure inside the balloon is a little higher. It's air still, but it's a little higher pressure inside there than it is outside. And that extra internal pressure pushing out manages to keep the elastic skin at bay. Well, that begs the question, how do you increase the pressure of air? What can you do to it to make the pressure higher? Well, remember, the pressure is due to little particles bouncing around, hitting stuff, and they hit every surface statistically. And if you want to increase the pressure, you have to increase either the frequency with which they hit the surface, those particles hit the surface, or have them hit harder. You have two choices. And to make them hit more frequently, one way to do that is just to pack more of them into the same space. So space, we measure space in terms of volume. So this balloon has a certain volume of space, and if we put ordinary outside air into that volume, and it's normally as it's normally constituted, the pressure will be atmospheric inside as it is outside. So I should say atmospheric pressure is the ambient pressure of the local air. So it's the pressure of this air right now. If I put normal air inside the balloon, it's going to have atmospheric pressure, just like out here, and that's not going to be enough for the skin of the balloon. So what we have to do is put air in there that has more particles in it, in this volume than it would normally in the outside air. A way of measuring the amount of air in a volume is to say how much mass is there in a volume. Mass per volume. That's a quantity known as density. And the density of ordinary air here near the surface of the Earth is about 1¼ kilograms per cubic meter. So if I take the air, if I make a cube of air, chop it out about like that, it's a big one, and shook it, and I have to get everything else out of the way, so it's hard to shake it, I would discover, oh, it's about 1.25 kilograms of mass. That's not nothing. So air's got some substance to it. It's got some mass. And if I put that same air, just like that, with that density in this balloon, I would have atmospheric pressure air in here. But what I want to make the balloon hold up here, stay inflated, is I need more than atmospheric pressure air. So I want to put in more than atmospheric density of air. I pack the air molecules a little tighter than normal. And so the air inside this balloon might have 1.3, let's say 1.3 kilograms per cubic meter, a little more than the surrounding air. So increasing density, the basic idea, if you increase the density of the air or of any specific gas, pick a gas and stick with it. If you increase the density of the gas, its pressure, and do nothing else, its pressure increases. And if you double the density of the gas, that is, you pack twice as much gas in the same volume, you typically double the pressure. That's a very close, the relationship isn't perfect, but it's pretty close. So the pressure of the gas is proportional to the density of that gas. Double the density, you double the pressure. Multiply the density by 100, you raise the pressure by 100, and so on. So that's one way to increase the pressure of gas inside here. What's another way to do it? Temperature. If you increase the temperature of the gas, let's stick with air here, so let's increase the temperature of the air. When you do that, the particles now have more thermal energy on average. Thermal energy is distributed statistically, and it turns out that the average thermal kinetic energy of the particles, that is, look at the particles, only their kinetic energy is what you pay attention to, and you take the average kinetic energy of those particles over time. You watch them for a while, you watch a lot of them, average it out. That's exactly proportional to temperature. There's a little hitch, though, I'll come up to in a second. So that means that if you double the temperature of the gas, you will double the average thermal kinetic energy of the gas. And if you work out how that affects the bouncing and hitting and the momentum transfer and therefore the pressure, it turns out that as you heat up the gas, so some more average thermal kinetic energy, the particles hit more often because they're going faster and they encounter a surface more often, And when they hit harder because they're traveling faster and they bounce harder. So when all the dust settles, it turns out that the pressure of a gas, all else being kept the same, is proportional to temperature. Double the temperature, you double the pressure. So we saw, and I'm going to come to the hitch in a second, we saw that doubling the density doubles the pressure. Doubling the temperature doubles the pressure. This assumes, in each case, that you didn't do the other as you did the one. So when you double the density, keep the temperature the same. When you double the temperature, keep the density the same. If you double them both, the pressure goes up by a factor of 4. It's not, it's not rocket science. It's pretty straightforward there. Okay, the hitch. The hitch is temperature. What scale of temperature are we going to use? And it turns out to do what I just said, what I just said to be true, for doubling the temperature, giving you doubling the pressure, you have to use a specific type of temperature scale. A temperature scale in which 0 is the real 0, what is known as absolute 0, the lowest temperature you can go to, the temperature which there is no further thermal energy to be taken out of a system. So absolute 0 is very cold. In Fahrenheit, it's minus 459 degrees, give or take. In Celsius, it's minus 273 degrees, give or take. It's really cold. And we want to use that as the real 0 of a temperature scale. And there, fortunately, or not surprisingly either, there is a temperature scale that does that uses that 0 as its 0. It's called the Kelvin scale. It's not the only scale like this, but it's the one that we all use. And the Kelvin scale has zero Kelvin, and there's the word degrees left off. It's just 0 Kelvin. 0 Kelvin is absolute 0. And the spacing between the Kelvin degrees, there I go, immediately use it. 1 Kelvin, 2 Kelvin, 3 Kelvin, 4 Kelvin, that spacing is the same as the Celsius scale. It's just shifted. So if you work your way up to 273 Kelvin, you get to the 0 of Celsius. So it's a shifted version of the Celsius scale, if you will. And that means because the Kelvin scale is an absolute temperature scale, 0 is 0, that means that if you take the temperature of this air, which is about just short of 300 Kelvin, if you take that 300 Kelvin, if you double that temperature to 600 Kelvin, which is pretty hot, you get it in an oven that's really turned up high. If you had the same density of air in there, the pressure would double. This would, instead of having 1 atmosphere of pressure, this would have 2 atmospheres of pressure in there. So the basic observation then for this part of the story is that there is a simple relationship for a given gas between its pressure, its density, and its temperature. The pressure of that specific gas is equal to, or let's just say it's proportional to, because we don't know how you set the whole thing up. It's proportional to the density of the gas times the temperature of the gas on an absolute temperature scale. So that's you double either one of those things. Double density, double temperature, you double the pressure. Simple as that. Well, that gives us a lot about how a balloon is inflated. But now, if I want to see how balloons float, I need another bit of useful information. And that is to look at the air around us and look a little more deeply at what's going on here. Why is there atmospheric pressure here? What's creating that? And why doesn't the air just bouncing away, just doesn't bounce away from the Earth and head off into space? I mean, it's got something to push against down here, clearly, the floor, the walls and stuff like that. But by the time you go up, the ceiling's there, okay, but get rid of the ceiling, go out in the open field, there's something down below to hit, but there's nothing above to hit. Why doesn't the air just leave? Well, it doesn't leave because of gravity. The Earth's gravity is pulling down on the air, on the Earth's atmosphere, and keeping those little particles that are jiggling around from leaving. Occasionally they do leave, and in particular the littlest ones do leave, like the helium and hydrogen. Helium atoms and hydrogen molecules can escape from the Earth altogether. And that's one of the reasons why helium is a relatively rare gas in our atmosphere. It gets away. But neglecting that issue for the moment, the Earth's atmosphere is structured by gravity. The air is pulled down here. In the absence of thermal energy, the air would just flop as a sheet, a layer sitting on the surface of the Earth. But because of the thermal energy, it's propped up by the bouncing effect, and it pushes itself up into the sky, and it creates a structure in which there is high pressure near the ground and low pressure up above until finally it goes off to no pressure. There's a whole hierarchy of pressures sort of coming down, or at least the gradient of pressures. Where does that come from then? Well, the air down here, by virtue of its pressure, is pushing up on the air above it and supporting the weight of the air above it. And the air above that, by virtue of its pressure, is pushing up on the air above it. And if you think of air as blocks, say 1 cubic meter blocks here. In fact, I don't want to do that. Big rectangular boxes. Each box is pushing the boxes above it and supporting all of them. So the boxes down here, deep in the Earth's atmosphere, near the ground, are supporting an awful lot of boxes going on up, way up into the sky, kilometers up there. And so the pressure down here has to be pretty high to support all that weight. There is a lot of weight overhead. About 100,000 newtons per square meter of ground. That the relation, I observed that atmospheric pressure is about 100,000 newtons per square meter, and there's about 100,000 newtons of weight overhead of each square meter. Those are related, no duh. Okay, this air pressure here is supporting the weight above it. The air pressure up here is supporting the weight above it. It doesn't have to be quite as high as down here, because this one's supporting the weight of that guy and the ones above. This guy isn't supporting its own weight. It's supporting the weight of the guys above it. And above them, they have less and less weight. So the atmospheric pressure decreases with altitude. It's highest down here. If I could go lower in the basement, it would actually be a little higher down there than it is here. But it goes it runs the whole range from this pressure to this pressure to this pressure, all the way up until basically zero pressure, way up high. Tens of kilometers up there. So, an observation is that there is a gradient in the Earth's atmospheric pressure. The gradients point, they're a continuous variation in a physical quantity, and the gradient points towards most rapid increase in that physical quantity. So there is a downward pressure gradient in the Earth's atmosphere. This comes about because the densities are decreasing as you go higher. So the atmosphere down here is a little denser, a few more atoms and molecules per cubic meter than up here, and so on. So the densest atmosphere is down here, less dense up here, and it gets less and less dense as you go up toward the sky. This is one of the reasons when you go up high into the mountains, to an extent in plains, although they compensate for some extent, the air gets less dense. There are less atoms and molecules per cubic meter. Breathing it doesn't do you quite as much good. So some people start to have altitude sickness issues, or at 5,000 feet, 10,000 feet, 15,000 feet, you go up into the Himalayas, and everybody's got altitude issues. The air there is getting so thin. The density is so low. It's just there's not much. It's not doing you much good anymore. So the Earth has a pressure gradient. Again, the gradient points towards highest rapid increase. The gradient's downward, but that means that the pressure gets less and less as you go up in altitude. By and large, this is caused by a density gradient. The density is getting less and less as you go higher and higher. There's also a temperature effect. It's a detail the temperatures change with altitude too, and I'm going to leave that aside for the most part. It's primarily a density effect that we care about, and so there's the Earth's atmosphere. It has this continuous evolution of pressure, and that means that the pressure down here of the Earth's atmosphere is measurably larger than the pressure up here. They differ by enough that you can figure it out that it's real. It's actually there. Well, that means that if I put a balloon into the middle of this Earth's atmosphere, the pressure down at the bottom of the balloon pushing up is a little greater than the pressure at the top of the balloon pushing down. It's real. It's actually there. It's less noticeable in air than it is in fluids that are denser, that have more mass per cubic volume. The gradient gets stronger. There's more weight to support. And something like water has a very significant difference in pressure between deep in the water and less deep in the water. As you go into the water, the pressure rises fairly rapidly because the water down there is supporting the weight of the water up here. And you know, if you go diving, your ears start going crazy as you go deep into the water because the pressure is evolving so fast. All right, back to balloons in air. This balloon is really experiencing a little stronger upward force at the bottom due to pressure down here than it is downward force due to pressure up here. That difference in pressures and difference in forces overall creates a net upward force on this balloon due to the surrounding air and the pressure gradient in that air. That net upward force on the balloon has a name. It's called the buoyant force. And it's a new force. It's not a sort of a fundamental force in nature, no, but it's there for any object immersed in a fluid when gravity is present. So gravity creates this pressure gradient in the Earth's atmosphere, and once you got that pressure gradient, you got a buoyant force. And the buoyant force in this balloon pushes it up. Not enough to support its weight, but the net force on this balloon is pretty small because the balloon is almost supported by the surrounding atmosphere. Now, how in the world would you ever figure out how hard the surrounding atmosphere pushes up on this balloon? Well, it turns out there's an easy answer, and this dates back to Archimedes, rather a long time ago. Archimedes made this observation, that whether the balloon is here or a sort of virtual balloon is here, you can still visualize the balloon there, right? And that virtual balloon is just a blob of air that's balloon shaped. For your memory, this is what the balloon looks like. There's a blob of air just like it right there. And that blob of air is just hanging out at equilibrium. Nothing's pushing, net force 0. It's not falling. What's supporting it? The buoyant force. Okay, it doesn't have a skin like a balloon does, but who cares? It's still a blob of air that's balloon shaped, and it's not falling. So it's being supported by the surrounding air, and therefore the buoyant force. And what is the weight of the balloon? What is the weight of the balloon-shaped blob of air? Well, it's whatever the weight of the balloon-shaped blob of air is, and the buoyant force is exactly canceling it. So the buoyant force upward on that blob is equal in amount to the blob's weight, the balloon-shaped blob's weight, but in the upward direction. Well, the surrounding air doesn't know whether there was a balloon there or a blob of air there. Doesn't matter. That's So the surrounding air is pushing up on this balloon with a buoyant force that's equal in amount to the weight of the air the balloon has pushed out of the way, displaced. So that blob of air that would be there if the balloon weren't there, that blob has a weight, and the buoyant force is equal in amount to that weight. It's upward though. So that's the buoyant force on objects. Just look at the fluid they displace and weigh it. So this balloon has an upward force on it equal to the weight of pure air that's balloon size. Alas, this balloon weighs a little more than that. Why? First off, the air inside is a little denser than normal. In order to have that extra pressure to keep the balloon from collapsing, because of its elastic skin, so it weighs a little more than a blob of air. You know, the air inside weighs a little more than a balloon-shaped blob of air would. Second thing is that rubber skin is pretty dense stuff, and it adds a lot of weight to the balloon. So between those two, the slightly extra dense air and the balloon skin itself, it weighs more than the buoyant force can support, and the balloon goes down. How could we change that, though? Two ways come to mind. One of them is to take the air inside, reduce its density, which by itself would reduce its pressure and the balloon would collapse. But will reduce its density, but compensate by increasing its temperature. We'll make a hot air balloon. So instead of containing ordinary temperature air, slightly over the normal density, we'll have it lower density air that's hotter and still has the right pressure to keep the balloon inflated. You can do that. And that's basically what a hot air balloon does. In a nutshell, a hot air balloon fills the balloon with air that's hotter than normal and therefore has increased pressure just due to its temperature. And to get the pressure inside the balloon and outside the balloon to be essentially equal, apart from skin issues, you have to compensate. You're going to have hot air inside, which by itself would raise the pressure and blow the balloon up, reduce the density of the air. So there are fewer particles in every cubic meter, less mass as a result, and the air now has the right pressure. So density down, temperature up, product of two is the same, you're golden. But the consequence of having lower density air inside the balloon is the balloon weighs less. And so now you can have a situation where when you look at the buoyant force up due to the surrounding air and the weight down due to what's inside the balloon, well, the balloon's got less heavy stuff in. It's got low density, hot air inside, and the balloon would float. So that's what keeps hot air balloons up. Raising the temperature allows you to decrease the density of the air and therefore its weight per volume without having the balloon smashed by atmospheric pressure. How about helium balloons? Well, to explain how helium balloons work, I need to bring in another detail, and that is, to this point I've talked really only about air, or pick one gas and stick with it. But now we're going to talk about taking a different gas, helium gas itself. Helium gas consists of helium atoms, which are very, the second tiniest atom after hydrogen. So they have little mass and they have little weight, each little helium atom. And when you put them in a balloon, they can create pressure too, and they can inflate the balloon and keep it all puffed up and all that stuff. The question is sort of how many heliums are inside, how many helium atoms are inside, and therefore how much weight do they contribute to the balloon. And it turns out that if you start substituting helium atoms for air molecules or air particles in a box of in a box of air, so you start putting in helium atoms and taking out the same number of air particles, the pressure doesn't change. So you keep doing that until the box is entirely helium atoms, no air particles, and the pressure hasn't changed. The only thing that you've done is you've substituted one for one air particles, helium atoms for air particles. The result is that, the observation that you can take away that is that the pressure of a gas depends only on the number of particles per volume times the temperature, and not really on the density. The density measures mass per volume, and for a specific gas, that's very nicely connected with the number of particles per volume. Each particle has a certain mass, and you can figure it out. But if you change gases, the density rule isn't quite the right thing. It's actually the particle density rule. The number of particles in a volume ultimately determines the pressure there. And whether the particles you're dealing with are air molecules or whether they're helium atoms, you get the same contribution to pressure from every particle. What that means then is that a helium balloon, if I had two balloons here, I've only got one, plan ahead, but I didn't. Two balloons, one helium, one air, they contain the same number of particles, assuming they're the same size. The air particles, the helium, a bazillion and 3 air particles, a bazillion and 3 helium atoms. Balloons look the same. That's pretty cool. How do helium atoms do that? They're so much dinkier than air particles. How do they contribute the same amount of pressure that the air particles do? Well, it turns out that if you look at a helium atom, you give it its standard dose of thermal energy, like any particle, air particle or otherwise, it travels faster because it's got less mass. If it's going to carry the usual dose of thermal energy, it better move faster. It doesn't have very much mass to work with. So the speed's greater. A helium particle at ordinary temperatures travels at more like a kilometer per second. It's so dinky and it's so little mass, it really cuts a rug. So the helium atoms are traveling faster, they're hitting more often, they're making up for their small mass by really pounding into surfaces. And so despite the fact that they're dinky, they contribute just as much on a particle per particle basis as an air particle. So a helium balloon can be fully inflated if you put if you put the same number of helium atoms in as you would have normally put in air particles. The difference though is a helium balloon, when it's fully inflated with that number of helium particles, doesn't weigh much because helium atoms don't weigh much. And so when you've got a helium-filled balloon, it's inflated, it has the right pressure to keep itself from being smushed by the atmosphere, but it doesn't have much weight. So when you look at the buoyant force up and compare it to the weight down, the buoyant force wins, and the balloon experiences a net upward force, and up it goes. So that gives us then two ways to make lighter than air balloons. One of them is to just stick with air, but heat it up so that you can use lower densities and therefore have the balloon weigh less. The other is to substitute for the air, substitute in helium, which weighs a lot less particle for particle than air. But you only need to put in the same number of particles you would have for air. So you end up filling the balloon, but giving it much less weight than you would have. Helium, incidentally, is not the only lighter than air gas. Another one is hydrogen, a famous one, which is unfortunately flammable. Hydrogen particles are actually hydrogen molecules. They weigh half as much as helium does. So a balloon full of hydrogen and a balloon full of helium, the balloon full of hydrogen would weigh about half as much as the balloon full of helium, approximately. But the buoyant forces on them would be the same. So the helium balloon would be significantly have a significant upward net force. The hydrogen balloon would have a slightly more upward net force because it's got even less weight to interfere with the big upward buoyant force. So hydrogen floats slightly better than helium does. But methane is another common molecule around. The natural gas is lighter than air too. So you can fill a balloon with methane and it will float up. On the other hand, if you fill a balloon full of things like carbon dioxide, which is heavier than air, particle for particle, you end up with a balloon that's a real sinker. So that then is the story of balloons.